These NASA deep space images reveal how the universe will actually end and the date it begins. Intro hook. The James Webb Space Telescope launched on Christmas Day 2021. Its mirror spans 21 feet. It sits 1 million miles from Earth. And the images it has sent back have not just shown us the universe in more detail. They have helped scientists figure out how it ends. Not in theory, with a specific date. In September 2025, a paper published in the Journal of Cosmology and Astroparticle Physics by physicists at Cornell University put a number on it. Using data from 2 separate observatories on opposite sides of the planet, they calculated that the universe stops expanding in roughly 11 billion years and collapses completely in approximately 20 billion years from today. This video covers what the images showed, what the data behind that calculation actually is, and what the final chapter of the universe looks like from here to the end. Section 1. What Webb sees and why it overturned what we thought we knew. When you look at the night sky, you are not seeing the present. You are seeing the past. Light takes time to travel. The light from the moon left 1.3 seconds ago. Light from the sun left 8 minutes ago. Light from the nearest star outside our solar system left 4.2 years ago. The further out you look, the further back in time you see. Webb was built to receive the oldest light that exists. It does this using infrared detection. As the universe expands, it stretches the light passing through it. Light from a galaxy billions of years away started as visible light, but arrives as infrared, which human eyes cannot detect. The Hubble Space Telescope was built primarily for visible light. Webb sees infrared. That difference alone lets it peer back further than any telescope in human history. Webb's first deep field image, released in July 2022, showed a patch of sky roughly the size of a grain of sand held at arm's length. Inside that patch were thousands of galaxies. Some of that light had been traveling for over 13 billion years. In May 2024, Webb confirmed the most distant object ever observed, a galaxy called Jade's GSZ 14-0. Its light left just 300 million years after the Big Bang. The galaxy is more than 1,600 light-years across. It already contained enough mass and stars to be visible across 13.5 billion years of cosmic expansion. Astronomer Brant Robertson at the University of California, Santa Cruz described the discovery as completely unanticipated and likely to be seen as the most significant extragalactic discovery with Webb to date. Then, in 2025, that record was broken again. A galaxy called MOEM Z14 was confirmed at an even greater distance, roughly 20 million years older than Jade's GSZ 14-0. Peter Van Dockum of Yale University, part of the research team, stated that Webb was not expected to find any galaxies this early at this stage of the mission, and that there are very roughly over 100 more relatively bright galaxies in the very early universe than were expected before Webb launched. This is the problem those images revealed. The standard models of galaxy formation predicted that the earliest galaxies should have been small, dim, and slow to grow. Webb found the opposite. Large, bright, fully assembled galaxies existed just a few 100 million years after the Big Bang, far earlier than any model said they should. NASA confirmed these findings did not change the age of the universe, which remains 13.8 billion years. What they showed is that structure formed inside that universe far faster than anyone expected. And what drives the formation and fate of all that structure is a force no one has ever directly seen. It makes up 68% of everything that exists, and new measurements of it have just rewritten the most likely answer to how the universe ends. The force is called dark energy. What two major observatories found when they measured it across 11 billion years of history is what changed the calculation entirely. Section 2. What the universe is actually made of. Everything you have ever seen, touched, or measured with any instrument makes up 5% of the universe. Every star, every planet, every ocean, black hole, person, and gas cloud. Combined, 5%. This comes from NASA and is based on measurements by the European Space Agency's Planck satellite, which mapped the faint glow left over from the Big Bang with enough precision to calculate the full composition of the cosmos. The result? 5% ordinary matter, 27% dark matter, 68% dark energy. Dark matter is invisible. It does not emit, absorb, or reflect light. Astronomers know it exists because of what it does to the things they can see. Galaxies rotate at speeds that only make sense if far more mass is present than the visible stars account for. Light bends as it passes through regions of space where no visible matter exists. In 2006, scientists observed two galaxy clusters colliding and found that the visible gas was slowed by the impact, while the dark matter passed straight through untouched, providing some of the clearest direct evidence of its existence. We have mapped it. We have measured its gravitational effects. We still do not know what it is made of. Dark energy is harder to explain than dark matter. It is not a substance in any conventional sense. It appears to be a property of space itself, a pressure built into the fabric of the universe that pushes everything apart. The more space there is, the more dark energy there is, which means expansion generates more expansion. In 1998, two independent teams of astronomers studying distant exploding stars called Type Ia supernovae made the same discovery simultaneously. Saul Perlmutter led the Supernova Cosmology Project at Lawrence Berkeley National Laboratory. Brian Schmidt led the High Z Supernova Search Team, with Adam Rees playing a central role. Both teams expected to find the expansion of the universe slowing down under gravity. Both teams found the opposite. The expansion was speeding up. Supernovae were further away than they should have been. Something was pushing everything apart faster and faster. The 2011 Nobel Prize in Physics was awarded to Perlmutter, Schmidt, and Rees for the discovery of the accelerating expansion of the universe through observations of distant supernovae. That acceleration is dark energy at work. For 2 decades after 1998, the working assumption was that dark energy was a cosmological constant, a fixed number, unchanging across all of time and space. Albert Einstein had introduced the concept more than a century earlier. It fit every data set perfectly. The universe would expand forever, grow cold, and eventually die a slow, quiet death in permanent darkness. That was the settled picture. And then the instruments got precise enough to actually test it. What the Dark Energy Spectroscopic Instrument found when it mapped 47 million galaxies across 11 billion years of cosmic history is not what a constant predicts. And the difference is what drives the new calculation of when everything ends. Section 3. The instrument that changed the calculation. The Dark Energy Spectroscopic Instrument, known as DESI, sits on the Nicholas U. Mayall 4-meter telescope at Kitt Peak National Observatory in Arizona. It contains 5,000 fiber optic positioners, each independently aimed at a different galaxy, capturing 5,000 galaxy spectra in a single night. DESI was built to test one specific question: is dark energy constant? It does this by measuring what are called baryon acoustic oscillations. In the early universe, pressure waves moved through the hot, dense plasma that filled all of space. When the universe cooled enough for atoms to form, those waves froze in place, leaving a characteristic pattern in how galaxies cluster together. That frozen pattern acts like a ruler. By measuring how the ruler's apparent size changes across different periods in cosmic history, Astronomers can calculate how fast the universe was expanding at each point in time, and therefore how dark energy was behaving across those billions of years. In April 2024, DSE released its first year of results. The data covered 11 billion years of cosmic history. When combined with observations of the cosmic microwave background and supernova measurements, the results showed something no previous instrument had detected. Dark energy appeared to be weakening over time, not sharply but measurably. The cosmological constant, the one fixed number at the center of 25 years of cosmological models, was showing signs of changing. DSE co-spokesperson Alexei Leothod-Harnett of the University of California, Santa Cruz, said that what we are seeing is deeply intriguing. It is exciting to think that we may be on the cusp of a major discovery about dark energy and the fundamental nature of our universe. In March 2025, DSI released its second year of data. The preference for evolving dark energy over the fixed constant model increased to 4.2 sigma confidence. In astronomy, 5 sigma is the standard for a confirmed discovery, meaning 99.9999% probability the result is real. DSI's second year sits just below that at 99.995%. Nature Astronomy reported the finding as strengthened, but not yet decisive. That same week, results from the Dark Energy Survey in Chile and the Atacama Cosmology Telescope were published separately. All 3 instruments pointed in the same direction. Dark energy is not fixed. Something about it is evolving. Will Percival, co-spokesperson for DSE and a professor at the University of Waterloo, described the situation plainly. He said the simplest explanation for what they see is shifting. If dark energy is weakening rather than holding constant, the universe does not expand forever. Gravity, which dark energy has been overpowering for billions of years, eventually wins. Expansion slows, stops, reverses, and the entire universe collapses back into itself. Before we move on, if you're enjoying this analysis, please consider subscribing. It helps the channel tremendously. Cornell University physicist Henry Tai took the DSE and dark energy survey data, ran them through a theoretical model, and published a specific timeline. That paper appeared in the Journal of Cosmology and Astroparticle Physics in September 2025. Section 4. The date and what happens between now and then. Henry Tai is the Horace White Professor of Physics Emeritus at Cornell University. His paper, co-authored with Huangnan Liu and Yucheng Chu, entitled The Lifespan of Our Universe, was published in the Journal of Cosmology and Astroparticle Physics on September 18, 2025. Tai's model incorporates a hypothetical low-mass particle called an axion, which behaves like a cosmological constant early in cosmic history but changes over time. In this model, the cosmological constant is not positive, as had been assumed for 20 years, but slightly negative. A negative cosmological constant does not push the universe apart. It eventually pulls it back together. The timeline Tai calculated is as follows. The universe continues expanding for roughly another 11 billion years. Expansion reaches its maximum and halts when the universe is approximately 25 billion years old. Contraction begins from that point. The final collapse arrives when the universe is approximately 33 to 34 billion years old. The universe is currently 13.8 billion years old. The reversal begins in roughly 11 billion years. The end comes approximately 20 billion years from today. Tai stated this directly in the paper. This big crunch defines the end of the universe. He also said that for the last 20 years, people believe that the cosmological constant is positive and the universe will expand forever. The new data seem to indicate that the cosmological constant is negative and that the universe will end in a big crunch. He is explicit that this is not confirmed. The model depends on the DESI findings holding up as more observations arrive. Upcoming data from the European Euclid Space Telescope, which is already in orbit, from the Vera C. Rubin Observatory in Chile, and from NASA's SPHEREX mission will test these predictions in the coming years. If future measurements show dark energy snapping back to the standard constant model, the timeline changes. If they strengthen the DESI signal, the calculation becomes harder to dismiss. What makes the paper notable is not just the conclusion, but the specificity of the mechanism. Prior work had established that a negative cosmological constant leads to collapse eventually. That part was not new. What Ty's model added is specificity. It does not just say the universe will collapse, it says when. And it derives that timeline from real observational data from two independent instruments on opposite sides of the planet. The contraction, when it begins, is not gradual in the way the prior expected death was. The former leading model of the universe's end, known as the Big Freeze or heat death, stretched across time scales of trillions upon trillions of years. Under Ty's model, based on the DESI data, the entire collapse from maximum expansion to final singularity takes roughly 9 billion years. Galaxies begin approaching each other, and then they merge. Background radiation heats as space compresses, stars collide, black holes dominate the shrinking volume. Eventually, all matter, energy, space, and time compress into a single, infinitely dense point, reversing the Big Bang. The standard model that preceded this one, which held the field unchallenged for over 20 years, predicted a completely different ending. Understanding what that ending looked like makes the shift in the data more concrete. From 1998 until 2024, the consensus among cosmologists was that the universe would die the way a fire dies, not in a sudden collapse, but in a slow, permanent cooling that never stops. Under that model, dark energy holds constant. The universe keeps expanding forever. Within a couple of trillion years, dark energy pushes distant galaxies so far apart that no galaxy outside our own local group is visible from any other. The night sky empties. Star formation ends around 100 trillion years from now, when the raw material, dense clouds of gas that collapse under gravity, no longer exists. The last stars are dim red dwarfs that burn hydrogen slowly and take trillions of years to die. After them, only white dwarfs, neutron stars, and black holes remain. Black holes, the last major structures standing, slowly leak mass through a process called Hawking radiation, first predicted by Stephen Hawking. Quantum effects near the event horizon cause the black hole to radiate energy outward until nothing is left. A black hole with the mass of a star takes around 10 to the power of 64 years to evaporate this way. The largest supermassive black holes take around 10 to the power of 100 years, a number called a googol, or possibly longer. After the last black hole is gone, the universe contains only scattered subatomic particles and extremely low energy photons. The temperature hovers just above absolute zero. No reactions occur, no processes run. This state is called maximum entropy. Time effectively loses its meaning because nothing remains that can change. This is the Big Freeze. That model was not guesswork. It was built on the best measurements available for over 2 decades. It remains possible. If the DC signal turns out to be a statistical artifact that disappears under higher precision measurements, the Big Freeze returns as the leading scenario. What the 2024 and 2025 data introduced is a measurable tension with that picture. DESI used the largest 3-dimensional map of the universe ever made to track dark energy's influence over the past 11 billion years. And combining that data with other experiments shows signs that the impact of dark energy may be weakening over time, suggesting the standard model may need an update. DESI's second data release in 2025 showed a preference for evolving dark energy over a cosmological constant at 4.2 sigma significance. The question of which ending is correct comes down to a single measurement: the sign and stability of the cosmological constant. Positive and fixed means eternal expansion and a cold, quiet death. Negative or declining means collapse. DESI's combined data points toward the second. The instruments running right now will narrow the uncertainty substantially within a few years. The honest position is that the data is not settled. What is settled is that the question of how the universe ends is no longer an abstract one. It is a measurement problem, and the measurements are actively being made. Verdict: what the full picture shows. Take everything from the previous 5 sections and lay it out plainly. Webb found galaxies from 300 million years after the Big Bang, galaxies that assembled far faster than standard models predicted. That finding did not break cosmology. It revised our understanding of how quickly structure forms in the early universe, and it pushed astronomers to refine the models governing how dark energy behaved in that early period. DESI mapped 47 million galaxies across 11 billion years of cosmic history. Its first-year data showed hints that dark energy is weakening. Its second-year data, combined with separate results from the Dark Energy Survey and the Atacama Cosmology Telescope, raised that signal to 4.2 sigma. 3 separate instruments, independently built and operated, are pointing in the same direction. Henry Tye at Cornell used that data to calculate that the universe stops expanding in roughly 11 billion years and collapses in approximately 20 billion years from today. His paper was peer-reviewed and published in a major journal. He described the finding as a major departure from 20 years of cosmological assumption. He also described it as dependent on the DESI measurements holding up. What is confirmed? Dark energy makes up 68% of the universe. Its behavior over cosmic time is measurably inconsistent, at high statistical confidence, with a fixed constant. The standard model that predicted eternal expansion and a cold, slow death is under genuine observational pressure for the first time since 1998. What is not confirmed? Whether the DESI signal survives as precision increases, whether Tye's action model is the correct interpretation of that signal, and whether a big crunch in 20 billion years is actually where this ends. The Euclid Space Telescope, already in orbit, will provide independent measurement. The Vera C. Rubin Observatory in Chile is coming online. NASA's Spherix mission will add additional constraints. The answer to which scenario is correct will not come from theory. It will come from observation. And the observations are running now. The universe has been expanding for 13.8 billion years. The force driving that expansion has just shown its first measurable signs of changing. A Cornell physicist has calculated that it stops in 11 billion years. The most studied question in cosmology, how does everything end, now has a specific proposed answer for the first time. Whether that answer survives the next round of data is what the current generation of instruments exists to determine. The expansion began 13.8 billion years ago. Based on the DESI and Dark Energy Survey data, the model puts the big crunch at approximately 20 billion years from now. The clock is running. The measurements are being made. The universe itself is the data. If you enjoyed this video, make sure to subscribe. Thanks for watching, and we'll see you in the next one.